Hi, welcome to the Signal Path. In this episode, we're going to do an equipment upgrade. I've owned this HP Agilent 53131A frequency counter for some time now, and I think I used it in one of my previous videos. This is a 2-channel, 225 MHz, or 2 input channels, 225 MHz frequency counter, but it also has an available third option that allows it to go all the way up to 3 GHz, but you need the upgrade package to do that. Now, of course, I don't have that, and I take a look at Agilent website, and the upgrade kit is really expensive. It's not really worth it, especially because you can buy one of these from eBay for less than $700. So I said, well, we're not going to do it that way. Then I did some more searching on eBay and on some other websites, and some people have made a custom PCB that's essentially a knockoff, a replica of the Agilent upgrade kit that you can install yourself in here and have your unit go all the way up to 3 GHz and even beyond 3 GHz, making this a much more useful frequency counter. So I bought one from eBay, from a seller from Poland for about $100, which I thought was a really good deal. And then I wanted to install it, but hey, we can make a video about it and not just put the upgrade kit inside here and find out what it looks like and how it works, but I really wanted to reverse engineer the upgrade kit and do some measurements along the signal path of that actual module to really understand how it works, dig out the datasheet for all the components that are on it, and it should be an interesting learning process in the meanwhile, and then we'll put it inside the unit and do some measurements and make sure it works. So let's get started. So let's take a look at the upgrade kit, and this is what I received in the mail. It came with one PCB and a bunch of screws to allow the PCB to be attached to the inside panel of the frequency counter. So let's take a look at this board itself. So a single PCB with a coax cable soldered directly onto the PCB. At the end of the coax cable is a panel attachable BNC connector. This BNC connector has washers and nuts and so on, which allows you to attach it directly from the inside to the front panel of the instrument, and the end will stick out, which then you apply the 3 GHz signal onto it. So this is going to be the frequency counter input. And there's also a ribbon cable connected to this board, and this ribbon cable will plug into the main board of the frequency counter, where the signals are fed back onto the PCB, where the instrument then can do frequency counting on the higher signal. So let's take a little bit closer look here and see how this board looks like before we start reverse engineering it. There's a lot to learn just by looking at it like this. Well, first thing to note is that here where the input signal is applied, there appears to be the footprint for a connector, maybe an SMC or an SMB connector. I'm not exactly sure what type was intended to be here, but they have not populated it. Most likely because, well, this will save cost, because these connectors can be quite expensive. Instead, what they've done is that they have soldered the coax directly onto the board itself, with the ground soldered onto the ground around the connector and the center pin directly in the middle of the footprint. Now, it may not look like on the camera, but it's actually a fairly good soldered connection. I'm happy with it. At first I was worried that this was a flimsy connection, but it's not. It's reasonably well done. And then afterwards you can see a chain of passive and active components. So the signal path from here to here, no pun intended, is where we are interested to reverse engineer and find out how it works. But there's a bunch of other things to note. First thing to note is that this board is flooded with vias, and of course that's normal practice for microwave engineering, because what you want to make sure is that you have a really good solid ground between the top and the bottom of the board. And remember, when I say solid ground, I'm not talking about ohmic resistance, I'm talking about impedance. So here we want to make sure that this top and the bottom ground remain very good ground across all the frequency of interest of this board, which is up to 3 GHz or so. And then once you get closer to the signal path here, you can see that there is a very careful via stitching around all the ground connections that surround all the high speed or the microwave lines. And that's also normal practice, because you want to make sure that not only you prevent signals from escaping, so by creating a very good ground, but you also want to make sure that the impedance across this line is well behaved and constant. And in this case, the impedance is 50 ohms as we study the amplifiers that are on this board itself. So what we expect to see is a transmission line from here to here, a microstrip transmission line. This is not a coplanar waveguide. And so therefore on the other side of this board, we want to see a solid ground. And if I were to flip it over, you can see that is indeed what we see, that the entire bottom of this board is ground. And again, you can see the stitching very carefully, that the stitching surround a microstrip transmission line like so, and whenever there is a microwave component or wherever there is an amplifier, you bring the ground right there very close to the microwave component and making sure that the ground connection to that component is really well connected both to the top and the bottom of the board, making sure that there is no resonances and no impedance variations on the ground, because you definitely don't want that. And in between the amplifier stages, we have a solid ground where the transmission line will run over. So this will be a nicely behaved 50 ohm microstrip transmission line connecting all the components all the way to that last IC. So on this side, what do we see? We see some passives, some R's and C's, and we'll talk about that, some diodes. Then we have 1, 2, 3, 4 microwave components. So it's a 4-stage amplifiers. And all these microwave amplifiers are supported with a bunch of passives around it, as we will see in the datasheet. And then at the very end, it's connected again to a pair of diodes and then back onto this IC. And this IC is actually a divider, and we'll look at the datasheet for that. And there is another IC here, which is a voltage regulator, and a whole bunch of passives to support that. But there's some other really interesting things here to look at. There's some basic decoupling cap here and here, of course. But if you take a look here, each of these microwave components is going to require VDD. Now, how do we bring VDD to this? Well, the easiest way to do it would be to just bring the VDD line from here and have the VDD line all the way up to here and connect it to each of these ICs. But it's not so straightforward, because if you don't decouple this line very carefully, this line itself will behave like a transmission line, and it will have some impedance, and that impedance is going to vary with distance and location and whether it's shorted or open at the end and so on. So because this is a VDD line, you can't just take it to the end and leave it floating, because then you will have an open stub, and that open stub is going to have all kind of impedance variation, and you don't want to put that on the VDD of your amplifiers. That's never going to work. So what they've done is that they have localized stitched ground planes here. So there's 1, 2, 3, and 4 here. So these localized grounds, they're using them to decouple this little line here, which is our VDD line. On the other side, you can see these areas that are stitched with via. This is actually to bring the ground really well to the other side of the board, so you can decouple the VDD. So this line here is decoupled with these little decoupling caps distributed along the line. And that's really important, because it ensures that this line here will have a very low impedance that does not change with frequency, and that is what you want from both your ground and your VDD. You don't want your VDD, for example, to look like a characteristic impedance of 50 or 60 ohms across frequency. That would be terrible. So what you would want is you want to decouple that to make sure that it stays a nice solid ground. And if you don't do that and the impedance of this line changes, it can look inductive and capacitive depending on the length and the frequency, and that can cause not just oscillations, but it can cause notches in your frequency response, where your amplifier, for example, all of a sudden would have absolutely no gain at 1 gigahertz because it lands in a notch where the VDD is an open circuit, which would be terrible. So you can see nice decoupling all along the line at the beginning and at the end, and throughout next to each of the components that takes current from the VDD line to make sure that this stays a very good solid VDD. And then the signal at the very end is fed into our divider signal, and then a whole bunch of other caps and so on to make sure that there's a good solid VDD and ground for this component as well. And then it goes into this cable, which then is fed onto the unit. So what I've done is that I have gone ahead and I have taken a close look. In fact, let's zoom in a little bit if I can make sure this thing can focus. Come on, maybe a little bit further. Here we go. So what I've done is that I've gone ahead and taken the number from all these, part number from these components, did a little bit of searching on the internet, and found a data sheet for all the components that are on this board. And we're going to go through them right now to see if we fully understand how this thing works. So here I've drawn the block diagram of this board here on my computer, and then I have the board here. So let's take a look at a one-to-one look at all the components along the signal path here. So at the input we have the RF input, which is separated from the rest of the circuit by an AC decoupling cap, followed by an input impedance matching resistor. This is just to keep the input impedance well behaved into 50 ohms. Let's ignore that for a moment. So this AC coupling capacitor separates the DC voltages that you may apply to the input of the circuit, which is good because you don't want to interfere. You don't want to insert a very large DC voltage here, because there's protection diodes right after. So what do these protection diodes actually do? Imagine the signal RF is very large, larger than the amplifiers can handle. In order to protect the amplifiers, you can have clamping diodes, and these clamping diodes ensure that the input signal swing at this node does not exceed a certain amount. Now how does that work? Well, since we are AC coupled, if I apply a sinusoid at the RF input, this node will swing both up and down, above 0 and below 0 volts. If it exceeds above 0 volts by more than the turn-on junction of this diode, then this diode will turn on, and the impedance at this node will drastically reduce as the diode turns on, and therefore all the current will go through the diode itself, and the voltage here will be clamped to the forward junction potential of the diode, because it's an exponential function, and the IV characteristic is exponential. Therefore, this voltage will be quickly clamped to plus whatever this junction voltage is. The same thing happens in the negative cycle. If the voltage is too low here, and if it swings below 0 too much, then this diode will turn on, and as a result, it will clamp the voltage to the turn-on junction of this diode. So the signal voltage here is limited. And then the signal is applied to 1, 2, 3, 4 amplifiers. So the input decoupling cap and the resistor are right here. Input decoupling cap, resistor. The back-to-back diodes are here and here. And then it's followed by the 4-stage amplifier. So there's another decoupling cap there, that's this one, and there's 1, 2, 3, 4, 1, 2, 3, and 4 amplifiers afterwards. And that's how the signal path goes. Now, I'll pose a little question for you guys. If clamping the signal is so easy, then why not do it all the time? What is the disadvantage of this circuit? And I want you to discuss that in the comments if you're interested. Tell me what is the problem a circuit like this can potentially cause for your amplifier. So now moving forward, we have an amplifier here, here, and here, and here, and these are these 4 components, and I have found a data sheet for those. And if you look at each of these amplifiers separated by the next amplifier by a blocking capacitor. This blocking capacitor, the only purpose of it is to ensure that the input to this amplifier, the DC voltage at the input of this amplifier, can be independently biased from the output DC voltage of the amplifier before it. So this VDD through this resistor and choke inductor will bias the amplifier as well as its input, because it's internally taken care of, and then each amplifier is fully independent of the next one. This structure allows you to cascade as many amplifiers as you want in a row to get more and more gain. But because of the specification of this unit, 4 amplifiers is sufficient to have enough gain to meet the minimum required input power to this circuit to ensure the divider still divides. So a signal comes in, gets clamped, amplified, 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 one more time amplified, and then it goes in through another clamping diode, and this is to ensure that the output signal swing of this circuit is now not going to swing excessively too much in order to damage the divider. And this is a divider circuit at the end. The signal is again AC coupled into the divider. The divider accepts a differential signal. One side of it is not used, so we apply a single-ended signal into the divider, and the divided out signal comes out. And this divided out signal can be either divided by 64, 128, or 256, depending on how you configure the digital switches built into the divider. And then divider output then gets sent through this little ribbon cable back onto the unit, which then the unit can count that frequency because now it's low enough, which is it's within its own counting capability, and therefore you will get your value measured. So let's go back and let's take a look at the amplifier itself. Let's put that aside. So this is the amplifier that is used inside the unit. It is a cascadable silicon bipolar mimic amplifier. So the really nice thing about this particular amplifier is that, as the name suggests, you can cascade many of them in a row because they all maintain a 50 ohm impedance all throughout the chain. So if you look at it a little bit more carefully, let's look at some of its features. So it's a 50 ohm gain block. So it is 50 ohm input, 50 ohm output, and it has 7.2 dB of gain, and it has a reasonably good flatness, 0.5 dB all the way to 3 GHz. So this is indeed a 3 GHz amplifier with very, very little ripple in the band between 0.1 to 3 GHz. And it has a 10.5 dBm of output saturated power at 2 GHz, which means that if I were to completely saturate the input signal here, and put a very large enough signal, then the last amplifier, in fact even the first one, but the last amplifier would put out as much as 10.5 dBm of output power, which is quite a lot. And anyhow, that will be clamped by the diodes anyway. And here's a sample biasing circuit for this amplifier. All it needs is that it needs a blocking circuit at the input, blocking capacitor at the input, and a blocking capacitor at the output. And this completely isolates the DC voltages, so you can cascade many of these in a row, as has been done on this board. And then all you need is a biasing resistor and an RFC, which is here. It says optional, but they exist on this board. So the purpose of our bias is to control how much DC current will flow into the amplifier itself. Now this is a HPT amplifier. They don't tell you the circuit inside it, but I suspect it's something perhaps like a common emitter, common collector configuration and so on. But either way, whatever it is, they have taken care of the input and output matching to be 50 ohms. This R bias is not supposed to contribute, is not supposed to contribute to the output impedance. This is important to realize, meaning that the only thing this R bias is supposed to do is to make sure that the amount of current flowing to the amplifier is whatever you want it to be. After that, this inductor will choke the output and it will be an open circuit for all the frequencies of interest that this amplifier is supposed to operate in. So as far as this amplifier is concerned, once the input frequency exceeds 100 megahertz, then this part is an open circuit. You don't even see this anymore, and all you see in order for you to calculate the input impedance, the output impedance of the amplifier is 50 ohm, the input impedance of the amplifier is 50 ohm, the choke inductor is an open circuit, and the blocking capacitors will become short circuit. This is a very typical thing to do. In fact, if you remember, I did a microwave tutorial video before where I've showed you what a bias T looks like. This is essentially a bias T, enabling an RF signal to go this way and a DC signal to go that way and keep them completely separate from each other. A bias T is not supposed to contribute to the output impedance or the input impedance of the amplifier. It's supposed to be short and open for the frequencies that you want it to be. So if you look here, we can actually identify those components relatively easily. So here's our amplifier. That's this guy. There is a decoupling cap before it and a decoupling cap after it. Here's our choke inductor and here's our bias resistor. And that circuit is in fact repeated. You can see inductor, capacitor, amplifier, inductor, resistor, capacitor, amplifier, inductor, resistor, and so on and on. So this is a cascade of a whole bunch of those, and here's your diodes at the input and diodes at the output. So the circuit is actually really simple. All it is a bunch of amplifiers. So wait a second. Well, why would we even want to have these amplifiers in the path? Well, the reason will become apparent. The reason is because this counter, this frequency divider, has a minimum input signal power for which it can divide. If you don't put enough power into the divider, it will not divide. And this is because this is based on a static divider architecture. So you have to make sure that you put enough power into this divider before the output of the divider actually starts to oscillate depending on the division frequency that you're looking for. So, having said that, let's say that you want to measure the frequency of an input signal that's really small. Let's say it is minus 40 dBm. Well, if it's minus 40 dBm, this divider is never going to divide with minus 40 dBm, so you're going to have to amplify the signal. So what they've done is that they use a 4-stage amplifier, and if you look at this, the gain of the amplifier is about 7 dB per stage. So if you have 4 stages, you're going to have about 28 dB of gain, just almost under 30 dB of gain. So even if I were to put a minus 40 dBm signal here, the signal that appears at the input of this divider is going to be about minus 10 dBm, which is significantly larger and within the division range of this divider. Now, if I go to the data sheet of the divider, that will become quite apparent. So here it is. This is a Motorola 2.8 gigahertz prescaler, which can divide by 64, 128, or 256. And depending on how you configure the switches, you can get division ratios from 64 to 256. It works from, up to 7 volts you can apply to it and so on. That's not the interesting part. The interesting part is this thing. So here's the block diagram of the divider IC, which is this guy right here. So you can see right off the bat, it has a differential input, and I said before that we only use one of its inputs, and then immediately goes into a static divider. Now I'm not going to go into the architecture of a static divider, maybe we'll leave that for some other time, but essentially a static divider will divide by a factor of 2 when it's configured like this. If it's configured with the feedback path around 2 flip-flops, then it will divide by 4. So if you have divide by 2, followed by divide by 4, followed by another divide by 4, and then divide by 2 3 more times. So 2 times 4, 8, times 4 again, 32, 64, 128, and 256. So if I were to disable this one and this one, then it will divide by only 64. If I enable this one, it will divide by 128, and if I enable that one, it will divide by 256. And it has an output driver. So you can see the architecture is really obvious how this thing works. And for static dividers, making a divide by 2 is the highest frequency. So they have a divide by 2 right off the bat. There's a reason why they don't divide by 4 right off the bat, because they want to make sure that it is the easiest to meet the highest frequency division. So divide by 2 will have the highest frequency response in a way. So so therefore they have put a divide by 2 in the front, and then 2 divide by 4s in a row, and then followed by, as I explained. So this circuit sits right in here, which will take care of dividing our 3 GHz signal down to a measurable frequency range. Now if I continue, here's another very interesting thing. This is a very typical static divider behavior. So what this plot shows, it shows you input frequency versus amplitude. So this tells you that if you want this divider to divide by 64 or 128 or 256, at any of these given frequencies, you have to make sure that you give it at least this much power. So let me say it again. For example, I want this divider to divide at 1.2 gigahertz. This tells me that the minimum input signal power to the divider must be minus 35 dBm. If you are below minus 35 dBm, the divider will not react, will not divide to a 1.2 gigahertz signal. There is always going to be, for a static divider, some null like this, some frequency range in which even if you don't put any power in it, this thing will self-oscillate. This is the self-resonance frequency, the self-oscillation frequency of the divider itself. This self-oscillation frequency is a typical characteristic of a static divider because it is in positive feedback. The output of the output of the flip-flop is fed back to its input, inverted back to its input. This is Q and this is Q bar. So you bring Q bar back to the data, and you're driving the clock port of the flip-flop. This is in positive feedback. So this thing will oscillate itself, but it will oscillate at a particular frequency depending on the RC time constant, the technology performance, and if there are other components in there. It's a complex relationship which I don't want to get into, but the self-oscillation frequency of a static divider is a well-established behavior of these circuits. So this chain of dividers has a self-oscillation frequency of around 2 gigahertz to 2.4 gigahertz. So in here, even if you apply no signal to it at all, it will start to oscillate on its own, and it will divide that signal out. So it's really, so the frequency of operation for this guy, the interest of frequency operation is from here to around here. So which means that you want to make sure that you have at least about minus 15 dBm or so power into the divider, and all the way up to 3.2 gigahertz you will be able to divide any signal between these two frequency ranges. And that's why the amplifier is there, is to ensure that the input power to the divider meets this curve characteristic. And you can see they've even labeled an operating window here to tell you where you want to operate in a safe regime, because you want to make sure that you have enough margin, and with the variation from IC to IC, that you have enough power such that all of your circuits will always divide without having to worry. And that's what this operating window is there for. So having said all of that, we can see exactly what we're dealing with. So a bunch of amplifiers going into a divider like this, and the other component, there's one other component in here just for being thorough and complete. This is just a voltage regulator. It's a 5-volt regulator to feed this guy right here, because all the other amplifiers are running from 12 volts with an R bias, with a resistor that biases them. This guy needs 5 volts, so they have a voltage regulator there, and that voltage regulator is just this guy. Something very basic, nothing fancy. This one that I have is a Texas Instrument one, is an LM7805. So it's very basic. It's in a BGA package. So this one comes in a BGA package, but this has a surface mount. So there it is. That covers everything, and I think that we now have a fairly good idea of how this thing works. We know exactly the architecture. So now the only thing left to do is to do some measurements on it. So let's prepare to do some measurements. I've taken the front panel, the cover of this unit off, and I think probably all of you have seen what the inside of this unit looks like. Other good bloggers have shown the inside of this unit more carefully, so I'm not going to go into the detail of that. The only couple of things I'm going to point out is that this unit is equipped with the option of being able to have the inputs from the back. I'm not sure if that's standard or not, but either way, the signal can be either taken from the front panel or from the back, and there's a bunch of relays here in the front that allow you to switch in and out which exactly path it comes from. This one also comes with a high stability reference. So if you don't have the high stability reference option of this unit, then you'll be missing this, and it's going to have a typical crystal oscillator at the back of the unit which you can adjust. But this guy actually gives you a much more stable reference that allows you to make a much more stable frequency measurement. Because remember, the way this unit works is that it compares the input frequency with its own reference frequency, and it takes this reference frequency as the absolute frequency, and by that comparison it can tell you what your input frequency is. So by having a very good oven control crystal oscillator stable reference, you can make more accurate measurements. Now, I don't have, unfortunately, something like a rubidium frequency standard to calibrate this, but I think it should be in a fairly good calibration. If somebody has a rubidium standard they want to lend me, I'd be more than happy to calibrate this and then return it back to you guys. So now what do we do? Well, this thing is supposed to sit, let me flip it over. There it is. This thing is supposed to normally sit here, and it's supposed to connect to this connector right here. And then once you do that, then you take this little blocking thing out, and then the thing will stick through here. So in fact, I'm going to try and take that out afterwards. So what we're going to do is we're going to try and install this in here. But I've put these long legs on here so I can rest it on the side of the unit, and then that way we can actually measure it while it's powered on, because it's going to be very difficult to reach it if I were to install it, and that's why I added those legs to it. So let me set that up, and then we will do some interesting measurements on it and see if it does what we expect it to do. There it is. So all I've done is that I've plugged the cable back onto the unit, and this is the end of the business. This is where the signal is supposed to be applied, so that's where we're going to apply the signal. Now the reason I'm doing this way is because I want to apply power to the board. I want it to be operational, but not sitting inside, so I can easily measure it. Now, measuring this is not so straightforward. I wanted to measure the signal along the signal path, but you can't just probe it because this is a very high frequency signal, and you would have to have an oscilloscope with an active probe or a passive probe that works all the way up to several gigahertz. Now I don't have that, but I do have an active probe that works up to 3 gigahertz with my spectrum analyzer. So what we can do is we can apply a signal here, we can apply a signal to the input, and then we can measure it along this path. But we can do even better than that, because my spectrum analyzer from Rigo has a tracking generator built into it. So we can put a tracking generator signal in here and actually measure the frequency response along the path and de-embed all the other losses by normalizing the waveform using the active probe. So I've plugged this in. I'm going to show you exactly how that process looks like, and there are some important decisions to make along the way. One other little thing to note is that when I plug this unit in, obviously you have to be very careful, but the fan is running. And the reason is because even when the unit is turned off, as it is right now, the oven controlled crystal oscillator is powered. And so some part of the power supply is always on, and it turns this guy on. And the reason they do that is because they want to make sure that the oven controlled crystal oscillator remains warm for the entire duration when this unit is being used, not only to improve its stability versus time, and also to improve the unit to be ready. When you turn this thing on, you don't want to wait 30 minutes before you can make a super accurate measurement. Also, it helps the oven controlled crystal oscillator to remain in spec if it's kept at temperature over a very long period of time. So I don't care about that personally, so I don't leave it plugged in because the noise is too much, and also I don't want to use the extra electricity for no reason. So I usually don't have it I have a little switch that I turn off to make sure this is not always powered. But if you do have one of these, keep in mind that with this option the fan will always be running, so take that into consideration. So let me get ready for the rest of the measurement, and we'll see what we do. So let's make some measurement decisions. I said that I'm going to use the Rigo DSA 1030A spectrum analyzer with a tracking generator, and this guy has a built-in tracking generator, so we're going to use this. But what power should we use when we want to measure the performance of this amplifier chain? Now this may seem like a very simple thing, but a lot of people make mistakes when they're measuring amplifiers, because you have to really be careful about what input power you're going to test your amplifier with. This is even more important when you're measuring S parameters. Now, we're not doing a vector measurement, we're doing a scalar measurement, but nonetheless that's really important. And now let's walk through that. We looked at the data sheet of these components. We know that each of these amplifiers, little amplifier, has about 7 dB of gain. So 4 amplifiers in a row is going to have about 28 dB of gain. Let's say 30 dB of gain, even though it's going to be less because there are losses associated with the traces and the passives. But say 30 dB. So if this thing has a 30 dB gain, and we also looked at the output compression, the P1 dB of one of these amplifiers was about 10 dBm. Meaning that we don't want to operate near P1 dB. We don't want to measure this small signal gain of this amplifier near its compression point because we're going to be measuring its large signal performance. We will do that separately. First, we want to see its small signal performance, which means that we have to make sure that the output power of the last stage of this amplifier chain is kept sufficiently below 10 dBm. Let's say that I want it to be around 0 dBm, and there is 30 dB of gain, which means that I have to make sure that the input power to this amplifier chain has to be at least minus 30 dBm in order to ensure that the output power of the last stage remains less than 0 dBm. And if I do that, then I will make sure that all of the amplifiers are operating in the linear region, and I will get the small signal gain. And then later, if I want to measure the large signal performance, I can increase the input signal power to make sure that I can saturate the last stage. That way I can measure P1 dB and Psat, saturated output power of the amplifier, which is a very, very different measurement. You have to keep that in mind. Not only will the impedances change, but also the behavior of the circuit, the frequency response of the circuit is very different in large signal than it is in small signal. So you have to take all of those into account when you're making a measurement like this. So there's a lot of things to take into consideration. So for me, that's easy to do. Well, partially easy to do, because what I can do is I can go under source and I can change the tracking generator level that comes at the output. So I can reduce it. But behold, this guy only goes down to minus 20. So I cannot reduce the tracking generator's output level to below minus 20 dBm. Well, that's okay. That's not a problem. We can set it to minus 10 dBm. We can go to minus 10 dBm. And I have here a 20 dB attenuator. So I can add a 20 dB attenuator at the output of my tracking generator, and therefore reduce the power coming out of the attenuator by another factor of 20 dB, and that will give me minus 30 dB, which is exactly what I want to do, use to test this circuit. So let's connect this up. We're going to connect a little BNC to SMA at the back of this. We can connect our attenuator right here. So there we go. So now we have minus 20 dB, and then we have to connect this guy to the input of the tracking generator. So let's do that. And for that, we'll use a type N to SMA connector, like so. And then we have our cable. This is actually a really good cable because this is actually a K connector, but anyhow, we are using a very good cable for a very low frequency measurement. But I know some people who will be very unhappy knowing that we're doing this. So here we go. Connect this here as well. There it is. So now we have our tracking generator directly connected to the input of our little option module here. Everything now, again, I'm tightening these with my hand. You're supposed to tighten it with a torque wrench, but again, be cautious of these things. They matter quite a lot. I'm sufficiently tightened them, and this is not that high of a frequency, so it's not a big deal, but take that into consideration. So there it is. So our signal will come from the tracking generator. We'll go through here, we'll go through our 20 dB attenuator, will then be applied to the input of the amplifier, be amplified by the amplifier chain, and I want to measure it across there. But of course, this is a 50 ohm environment. I can't just take a cable and connect it from the input of the spectrum analyzer to that. Of course will not work, because you're going to interfere with the output impedance of these amplifiers. You want to maintain a 50 ohm environment. So what you do, you use an active probe. An active probe will have a very high input impedance, and therefore by connecting it to these nodes, you will not change the impedance by too much. You will change it a little bit, but not sufficiently to interfere too much with your measurement. And you've already seen my active amplifier, active probe before, so that's fairly straightforward. We're going to connect this guy to the spectrum analyzer, and this is powered, and the spectrum analyzer will power this thing for us. and I'm going to show you how that is done. You gotta be careful with these active probes. Not only are they quite expensive, but also quite sensitive. There we go. Plug this guy in here, as such. There it is. Now this is powered, of course, by this, and now we will connect this guy directly to the probe power port of this instrument, like so. And we want to make sure that the probe power is enabled, and we can do that by looking here. So there you go, probe power on and off. So it is indeed enabled. Escape that. So now here's the output of our probe. So the output of the probe, this probe has an extra 10 dB attenuator already at its output, so I don't need that, so I will remove that. And that's the input of the probe. And what I will do is that I will connect this little attachment like so. This little attachment would allow you to measure reasonably high frequencies with an RF input and a ground right next to it. So this is actually really convenient for us in this case, because what I can do is I can connect this ground to one of the vias that is right next to the microstrip transmission line, and I can probe one of the passive components and measure the signal along the path. So we will connect this guy to the output of this carefully. Make sure it's connected properly, and here we go. So now I will go to the source, and I will go ahead and enable the tracking generator, and its output set to -10, and we'll go on the normalize menu so I can normalize it afterwards. So we go down here. Now what do I want to measure? Well, what I want to do is I want to probe this signal along this path, but I want to do a relative measurement. So I want to measure the signal that arrives here, and then I want to measure the signal after each of the amplifiers and see how the signal is amplified. So what I'm going to do is I'm going to rotate this a little bit, make it a bit easier, and do a measurement on the input like that. So I had to tape the board down a little bit because it was moving around too much. It's quite difficult to probe it. So what I'm going to do is I like to probe the very input of this board. So that allows me to then normalize the waveform on the spectrum analyzer, and then have a measurement that's relative between each stage of the amplifier. So I'm going to go ahead and probe the input as carefully as I can, and I'm going to show you what it looks like. There it is. So that's what it looks like. So that's the response of the front of the unit. Again, it depends on how well I probe it. So let's go ahead and normalize that. If I normalize this, now this is my reference. So every measurement I do from now on is with respect to this zero line. So now I can actually go ahead and measure the gain of each of the amplifier stages really easily. So all I need to do is now remove the probe and then go to the output of the first stage. So now I'm normalized to the input. So after the first amplifier, I can measure the output, and then I can measure it again and again and again and find out what the signal is at the input of every other amplifier. Therefore, I know the gain of each stage. So I'm going to go ahead and go to this point. I'm going to probe that point as well. Let me get a good connection here. And there. Now take a look at this. What did we say? We said that the data sheet said that the gain of this amplifier is about 7 dB per stage. And you can see that it is indeed, it has about 7 dB of flat gain. I mean, it's not very flat, it's because I'm not probing it really well, but you can see it's 7 dB around here and 7 dB around here. So it's actually a very nice frequency response of the first stage of the amplifier. So now let's go, I'll remove the probe. I'm going to go to the input of the third stage. So now we have two amplifiers in a row, and we can look at the gain. There it is. Now the gain has doubled. Now we have in some cases almost 14 dB of gain. So now we go to the stage after that. If I can get a good connection here, there it is. Again, it depends on how well I probe it. There we go. Now we have about 21 dB of gain. And then finally, at the output of everything, I have here, if I can get a good connection from here to here, and we have about 28 dB of gain as we said. So again, the frequency response is not going to look very good because I'm not probing it really well. It depends on how well I can make contact. But what is really important to note is that at the very output of this amplifier chain, so I'm going to go all the way to essentially the input of the divider chain, and here's the input to the divider chain. You can see we have significant gain across the entire bandwidth that we expect from this module. So we have, you can see here at low frequencies. Now probing here is more accurate because it's easier to probe at lower frequencies. You can see we have 30 dB of gain, which is exactly what the datasheet said. The datasheet said that each stage has about 7.2 dB of gain. There's 4 stages in a row. Well, it's almost 30 dB. So we can see it indeed does match the datasheet. So we have confirmed, based on our quick probing measurement, that indeed the RF signal is growing at a rate of about 7 dB per amplifier across frequencies from DC to 3 GHz in this amplifier chain, and it is in fact working. So what is left to do is to put this back in the unit and do an actual measurement, see if it's actually measuring frequency as it is supposed to be measuring. But there's one other thing I wanted to do. I wanted to increase the input signal power and then see if indeed we have about 10 dBm of output power from the last stage or not. So I went ahead and I removed the attenuator, so we no longer have an attenuator, and I went ahead and I increased the power of the tracking generator to 0 dBm. Now what does that tell? What does that mean? What's the significance of that? Now we're putting 0 dBm into this amplifier chain. If I put 0 dBm into this amplifier chain and the output compression of each of the stages is only 10 dBm, I can't expect to get much more than 10 dBm from the last stage of the amplifier chain. We can verify that and see what the saturated output power of this amplifier chain therefore is. And I can do that again by following a similar procedure. I'm applying the signal right now. I will go ahead and I will normalize. Now remember, now I'm doing large signal because I'm putting 0 dBm into the amplifier. And if you look at the spectrum analyzer, you can see that the trace is now around 0 dBm. So now I will go ahead and normalize this again. There we go. Now this is our reference line, but now 0 dBm, all the amplifiers are going to operate into large signal. So I will go ahead and measure the very last stage again. So I'm going to probe the very last stage, like so. Look at that. Now if you were doing this from the very beginning, you would think that all the amplifier chains therefore have much less gain, but that's not true, because this is a large signal gain, meaning that if I'm putting in about 0 dBm, the output is about just under 10 dBm, as to be expected. There are some losses associated with the probe. I haven't calibrated that out, but anyhow, aside from that, you can see that this thing indeed can put out about 10 dBm of output power. Now remember that the output here is clipped also by the diodes, so this is probably not the saturated output power of the amplifier, but rather the clipped output from the diodes. If I go one stage further back where there are no diodes, let me see if I can get a better measurement. Oh, it looks like I'm actually saturating the probe. I am, in fact, saturating the instrument. So let's go ahead, put it here, and let me go ahead and set the amplitude level to 10 dBm. There you go, that corrects the problem. So there it is. Now we can see the saturated output power better because we don't have the diodes anymore. You can see it's above 10 dBm. So at higher frequencies, I'm getting 12, 13 dBm, which is a lot of power coming out of a single stage. So I'm now probing the output of the second stage. I'm putting in 0 dBm into the first stage. That's going to have 7 dB of gain. So 7 dBm is going into the second stage, and the second stage cannot put out 17 dBm because or 14 dBm is putting out just under 14 dBm. So this is the saturated output power of each of those amplifiers. And indeed, it is in fact working. I can go to the third stage. You can see that the third stage I'm getting about 14 dBm or so out, which is what we expected from the datasheet. So everything seems to work. Now the reason I did this measurement is because I want to highlight the difference between a small signal measurement and a large signal measurement. You saw the small signal gain of the amplifier chain was about 30 dB, we measured that, and we saw the saturated output power of the entire chain to be about 13 dBm or so, 12 dBm or so, which is again, everything matches the data sheet, so it works really nicely. Now the only thing we haven't tested is whether this divider is working, and that's easy to test. We'll put this guy back into the unit and then we can see if it measures the frequency correctly but using a signal source. And here we go, I installed the unit. That wasn't very exciting for me to film, so I am just showing it to you after it's done. It's screwed to the panel at the back. Here's the RF signal going in, and I tucked the ribbon cable behind the board and then back down onto here. I didn't want to leave it in front of the board because remember the divided down signal goes through here. So now this ribbon is nicely tucked between the ground shield of the chassis and the ground transmission, the ground plane at the back of the PCB for the transmission line. So it's nicely tucked away. It seems to be nice and stable. Things aren't going to move around. So now the only thing left to do is to put the panel back. I'll put it back inside the lab where it belongs, and then we will measure some frequencies, see if it works. So I've gone ahead and put the frequency counter back in the lab, and I have connected the new option that we installed from the front panel with an SMA cable to a signal source. Right now it's set to channel 1, and I can go to channel 3 now that the channel 3 option has been installed, and there is no signal, so it will show nothing. The signal generator is an Agilent 53131A. It's one that I picked up from eBay and repaired recently, so it's going back on eBay. But before I do that, I thought I'd use it for this measurement because it goes up to 4 GHz, so we can really stress the frequency counter all the way to its maximum frequency. So right now the synthesizer, although you probably can't see, is set to 100 MHz with 0 dBm of output power. So I'm going to enable the output. There it is, and voila, we see 100 megahertz, well, almost 100 megahertz. We see 100 megahertz and 91 hertz, 0.7. Now, whether this is inaccurate because this source is inaccurate or because my frequency counter is inaccurate is I don't know, because I haven't calibrated the frequency counter recently. And as I mentioned before, if any of you guys have a 10 megahertz rubidium standard that I can borrow for a couple of days to do a quick calibration and send it back to you, I would appreciate that. So let me know. So here we go. So now we can increase the frequency. Right now it's at 100 megahertz. We go 200 megahertz, no problem. 300, 4, 5, 6. And we go faster, 1.7, 2 gigahertz. Is that 2 gigahertz? Yes, it is. We go 2.6, 2.8, 9, 3.1, 3.2. So now it's beyond this specification because it's only rated up to 2 gigahertz. Rated up to 3.3 gigahertz, I meant. So at 3.2 gigahertz still works. We can go a little higher. 3.2, 3.3 still works. 3.4 still fine. 3.5 you can begin to see that the divider is not working anymore, so it's kind of making mistakes. So at 3.4 was still fine. 3.5 is not. If I go to 3.6, now it's completely broken up, and if I go any higher, then it gives me completely erroneous results. So right now it's set to 3.7 gigahertz and 0 dBm, and it's of course not working. So you can see that its range of operation exceeds that of what it is specified for, at least for 0 dBm. So that works. But there's one other measurement that I wanted to do. I wanted to measure the sensitivity of the divider, because we have the sensitivity curve of the divider, and we have already measured and we know the gain of the amplifier chain that's before it, so we can make some educated guess about what would happen at a certain input power before this unit cannot tell us the frequency anymore. So let me go back to some low frequency. Let's go to 400 megahertz, for example. Here's 400 megahertz, and I'm going to have the output power. Right now the input power to the unit is 0 dBm, which is very large, so let's keep reducing that. So 0 dBm, right now I'm at minus 10 dBm, still no problem. We go lower, this is minus 20 dBm, no problem. 30 dBm, no problem. Minus 40 dBm, it still works. Minus 50 dBm, it is still okay. And minus, oh wait, there it is, minus 56 dBm, it doesn't work anymore. So at minus 55 dBm, it's still okay, it's kind of okay, it's jumping around a little bit, which means it's right at the sensitivity edge. But does this number actually make sense? So I'm putting in minus 55 dBm into the unit. Let's forget about the little bit of the losses of the cables, let's ignore that. And the gain of the amplifier chain is approximately 30 dB. So minus 55 dBm to a 30 dB amplifier gain becomes minus 25 dBm, which means that at the input of the divider, we are having minus 25 dBm, and that's right at the border when the divider no longer divides. Well, let's take a look at our curve again. Here's our curve, here's frequency, here's input power. Look at that, 400 dBm minus 25 dBm. 400 megahertz minus 25 dBm. It's almost exactly this number that this graph says. So at 400 megahertz minus 25 dBm is right at the sensitivity curve of this static divider. And it makes perfect sense with measurement. It doesn't happen very often where your measurement matches so well with the datasheet, but here it is. It's exactly as the datasheet says, and it's exactly as the gain of the amplifier is supposed to be. So it works really well, and it is what we were expecting it to do. So I think that's more than you'd ever wanted to know about option 030 of the HP 53131A, but now you do. So if you have any other comments or questions, make sure you post it on the website, and I'll try to make some more videos. I have a whole bunch in the queue. Well, keep checking, and I appreciate all the kind words and the comments and the messages that you send. So I'll see you guys soon.